Beep, 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 beep. Are we done? Are we good? All right, okay. So our next speaker is a hardware software engineer who has been fascinated with AI and robotics throughout a 30-year professional and academic career. Now he'll be applying FPGAs to those areas, latest areas of work, which explores FPGA opportunities for hobbyists, makers, and hackers. So today he's going to show us how FPGAs will revolutionize small electronics, ostensibly conference badges. So please welcome to the Hackaday stage, David Williams.
Thank you very much. So about a year ago, I was busy contemplating the idea of building a quadruped robot. And I was very excited by the idea of this particular layout. So I thought of building the different gates, and I was like, oh, this is great. I was thinking about how to do frames for those robots, a combination of 3D printed joints and stock materials, and thinking about giant human-scale joints for the limbs with giant stepper motors inside. And I ended up with an architecture that looked a little bit like this. So taking a look at one of those limbs there, you got 1, 2, 3, 4 motors at least, and the motor controllers to run them, sensors to try to give feedback for the joints, and all manner of stuff sitting on this network. And of course, this network's duplicated for every limb. So I realized I had a bit of a SAD, that my RS-485 network, which I could coax up to about 4 megabits per second, was really not going to cut it. And then I kept bumping into this problem that the microcontrollers that I have at all of the nodes, I just want to put more and more stuff on them, and there's not enough GPIO on there. So I became FPGA curious. Now, FPGAs have been around for almost as long as I have, and they are, in my mind, they were sort of an intimidating thing that maybe hardcore EE engineers would use. So I hadn't really looked at them at all. But then a thing started to happen in that some of these new boards would come out, like the tiny FPGA BX, shout out to Luke, and the FOMU, and the Icebreaker. These parts are cheap. And suddenly I was starting to think, hey, maybe I could get into this. Maybe it's not so hard after all. And then, of course, the cream on the cake was that the big tools that the manufacturers have been delivering were the only way to do FPGA programming. And now suddenly there was some open source tools so that you could run it from the make line, just do make files. And it was starting to get really easy. So let's take a quick step back. All right. Let's take a quick step back and let's say, what is FPGA? Now, of course, come here today and everybody's talking about what is FPGA, so I thought, man, maybe I'm going to have to delete some slides and so on, but turns out what I have to show is a little bit different. So when my dad was doing electronics, which he did in the garage, electronics that he was using would be made up of discrete logic units. So this is something I just pulled out of a magazine, but it has the kind of elements that Dad would have been working with. So there's the 7-segment displays, there's the decoder chips that take the binary number and turn them into the appropriate signals for the displays, and then there are counters and a handful of other electronics. Each one of these, more or less, would have been a chip, which he wired up on a printed circuit board. And we all know what happened next. We had the microcontroller, which now could substitute a programmable device instead of having all this discrete electronics lying around. This is one of the very earliest ones. In fact, I remember the data sheet for this in the old National Semiconductor book. 1974, 1 megahertz to 4 megahertz. And you can really see on the die there all of the parts that made this microcontroller up. And that brings us up to today, where we've now got these amazing units which have a ton of memory, which have fixed functions to some degree, I/O ports. So then there's FPGAs. They're a completely different deal. So let's look into that a little bit. As people have said today already, FPGA stands for Field Programmable Gate Array. And how you use them is that you describe in a language the hardware that you want to be present on the FPGA. That's often done in this programming language called Verilog. Looks a little bit like C, but then it's got some quirks that make you go, no, this is not quite C. The tools that you use will translate that Verilog programming language into a set of gates, some I/O, which I've got in the dark gray there, some functionality in the white boxes, and some interconnections. So that's the job of the first part of that process, is to say, if I've got a Verilog program, what gates are going to be used on that program? And then the next question is, how am I going to take that set of gates and pop it onto my FPGA? So here's where we can take off the top and have a little look at this. So the first thing the FPGA has is around the outside some logic that helps to talk to the inputs and outputs. Now it's not just a pad, because there's actually logic in there. Sometimes it can get quite complicated, but think about it as being the way that signals go in and out of the FPGA. And here is the grid of gates. Basically, each one of these white boxes is a more or less generic little mini computational unit. This is the sort of the vocabulary of the FPGA. And inside some of this organization, there will be some specialized units that do different things to be a little bit more optimized. So in amongst all the white regular gates, there might be, for example, these blue ones, which might be memory, or these orange or gold ones, which might be, let's say, some arithmetic done in a more efficient kind of way. So that's the layout of the functionality on an FPGA. And so then the question is, well, how do we get these things all talking together? And what the FPGA has on it is a set of sort of superhighways that run around the chip as just like highways that we would use today. They're basically trunk lines that go from one place to another. I've drawn them left to right and up and down, and in fact they kind of jiggle and wiggle a little bit, but that's the essence of it. Well, then how do we get the functionality onto this superhighway? Well, we have interchanges, and they're called switch boxes. So each one of these switch boxes sits and connects the functionality onto these sort of interconnecting highways. And you might ask, well, if all of this is so generic, how does each one know what to do? And the answer is each one has a little tiny bit of memory, and that little tiny bit of memory says, for this run, we want you to be a certain kind of thing. So this switch box should switch this to this, and this piece of logic functionality should do this or that piece of logic. All right. So remember we had our little program with the 2 inputs and the 1 output and the 2 logic units. The first thing, so this is the placing part. So this is the part where we know what our program is going to be like. Now we need to know how it fits on the FPGA. And the first step's pretty easy because we actually knew where the inputs and outputs were because we told the tools there. So we can place and allocate our functional inputs and outputs to a particular place on the chip. Next thing we have to do, a little bit harder to see, is we have to say, well, which one of the potentially thousands, and our badges have 44,000 of these little white squares on them, which one of these is going to be the one to do each particular function, and where is it going to be? And typically the way these tools work is they sort of lay the functionality out next to where they're going to be used because they do a little AI allocation algorithm to try to figure out the optimal placement. So now we have all of our functional parts placed. The next job is to say, well, how do they all route together? So again, the tool will just figure out, okay, so this switch box has to route our signal on here and do this and do that. And so now, for each one of these boxes, we know what we want it to do. So our little piece of memory has a record of what we want that piece of functionality to do when it runs. And together, those red little blips are called a bit stream, and they're the thing that we send to the FPGA to tell it what to do. All right. So now we have the story of how the FPGA is kind of put together. This is just a little bit of an overview of what the tools are called. So you take the Verilog, and you use a process called synthesis to turn up the interconnecting network, and then the place and route tool is the one that actually takes what you come up with and puts it on the FPGA. Pack takes that description, turns it into a binary bit stream, and then off you go. And the open source versions of these are highlighted here. Yosis you'll hear a lot of, Next PNR you'll hear a lot of. So I wanted to just show a slightly more realistic example and then show you some pretty pictures. This is a very simple module. It's basically an adder. There are a few inputs. There's a clock, which says, which creates the drum beat. A reset line, which says start again. And then an input and another signal that says your input is valid right now. And then the output is the accumulator. So basically what you're doing is you're saying every time we get a new value coming in here, we want to add it to the accumulator and then output it again. So here's the first thing Yosis does to this. It says, well, I parsed through your Verilog and I came up with some inputs on the left and an output on the right. There's an adder thingy, and then there's some functionality called proc. So what does the next phase do of Yosis? We're going to go through these steps, right? The next phase Yosis does is it says, well, I think there's some more to do with this. There's a multiplexer and some latches and so on. Yosis then cleans that up, makes a nice simple representation, allocates the functionality again. These are all just little, this is the Yosis working with the same representation at every step. Now you've got to strap in, because we've been using each one of these little boxes as a representation for many bits. So when Yosis is finally ready to say, okay, so now how many bits are we really talking about here? Things get crazy. So this is its first pass. It's saying, okay, now we've got a lot of bits. It starts to do some other processes on that. It cleans those processes up. It does some more processes. It cleans that up. It does some more processes. It cleans that up. Until finally, it reaches the configuration that's really going to get pushed down onto our FPGA. And we can take a little bit closer look at this just so you can sort of see what it looks like. You've got a carry unit, an add-in and a carry unit. We've got a logic unit here. We've got the output here with another logic unit. It doesn't really matter, what all this functionality is, but that's the end result of that little tiny program. So then the next exciting thing is, well, now we've got all this mash of parts that we want to use on the FPGA. How are we going to place it? Well, Diamond, which is the tool that comes from Lattice, is kind enough to show us. So this is an actual diagrammatical form of the die itself. The purple lines are the clock lines. The cyan lines, which you can barely see, are the actual code. So you can see right here and right now, our little program, our little adder, is using just the tiniest part of the functionality on this device. But let's go in and take a little look. So as we jump in one step closer, you can start to see that there's a little bit of activity on the side, on this edge right here. That is your input and output. There's a little bit of activity clustered around the middle area there, which is the adding and some of the latching that we're doing. So let's go in a little closer. We're starting to see some of the superhighway kind of notation there. And there it is a little bit more. So here's the thing that's super weird about, one of the many things that's super weird about FPGAs is that all those white boxes that you were probably thinking were the logic, they're the switch boxes. By far the most space on an FPGA is taken up by just switching stuff. Those little tiny boxes are the ones that are actually doing all the action here. So I think we can go one more step in here. So the highlighted red box there is actually the thing that's doing one of the adding stage, bit one of basically the adding there. So that's kind of like the dive into what the FPGA looks like once you've programmed it a little bit. So over the years, FPGAs, they started off being glue logic. So, okay, we've got this complicated piece of something, and we've got this other complicated piece of something, and we want to connect them together, and the FPGA can do the drawing between them of the dots. Then we added more and more functionality until we come to this interesting model, which is where we put a full processor, where we actually get the FPGA to do the bulk of the work for our projects. And of course, to do that, we need to put, or we might want to put, a CPU on this processor. Now, how the heck do we do that? It turns out, and if you heard Joran's talk earlier on today, turns out that there are people who are crazy people who have written entire CPUs in that Verilog language that we were talking about. And the tools that we just watched put that little tiny program that I wrote will actually work on these massive programs and turn them into massive nets of thousands and thousands of nodes and put it lay it into the hardware. And the beautiful thing about this is the entire interface to this CPU. So you have a clock, you have a reset line, and then you have a simple memory bus. And that's all that the CPU needs in order to start working. So what you do is you connect that up to whatever it is that you want else on your new CPU that you're making. Like you might have some USB port, you might have some general purpose I/O, you might have some RAM, et cetera, et cetera. So the white region there is the region that's now going to get pushed down onto the FPGA, and you can sort of treat that as like a microcontroller if you want. But you have full control over what peripherals that you want to put on it. You can tinker with it, as other speakers have mentioned earlier on today. The tool chain changes slightly too. So before you would use Yosis and NextPNR to take your Verilog and to turn it into the gates. Well, now you have another thing as well, which is the program that you want to run on that soft CPU. So you can take your C++ application or C application, compile it with GCC, do the regular object copy, and you get it ended up with a nice bin file, and you can pop that into the configuration along with all the gates. And now when you download your bitstream, not only do you have your gates and how they're all set up, but you also have a microcontroller with its code and even with its initial register values if you want to do that. So you've got this whole almost freeze-dried system which is going to get dropped into your FPGA. And you can write code like this. And for those of you who've been playing with the badge, you can see that it really is just this simple. On my website, you'll see a link for it later. I have this exact example and a nice little make file that'll take you from the beginning to this. And yeah, our badge is just one of those. So you have, instead of one Pico RV32, you have two. A bunch of peripherals are on the outside, and then some nice gadgets and LCD screens and so on the outside. So let's get back to this theme of this talk. So MicroFPGA is a fairly cheeky thing for me to coin. What I'm trying to coin with this phrase is to say, not the really big, ambitious, hard FPGA stuff, but the simple stuff. And maybe try to create an allusion to microcontrollers or microprocessors in the sense that it's nice and small. So remember, the problem that drove me to FPGA was like, how do I convert my nascent robotic architecture into something that's going to perform a little bit better and a little bit more like I want it to perform? So what will change? Well, first of all, we're not going to use microcontrollers anymore. They're too slow. They don't get me the speed that I want from a communication point of view. I can't do specialized connections, like I can't talk to a camera. I can't talk to things that I want to talk to in the way that I want to talk to them. And all their pins are fixed. So we're going to use FPGAs. We can still have a CPU in there, as we've just discussed. We can still write code. We have a ton of I/O. So as my joint started to want to have skin sensors and position and IMUs and so on, we can accommodate all of that stuff. And it's fast. It's so fast. If you program it right, you can have things happening 100 million times a second, no problem. You write the peripherals you want. And it's in the name. You can upgrade it in the field. So change the way the entire hardware is laid out, just right there. So how do you get started on this? Well, I don't recommend that you crack open KiCad and start to lay out these 381-pin BGA controllers. I don't recommend that. Luckily for us, there are actually many products at really reasonable prices which will let you build an FPGA into your project in the same way that you might build a microcontroller into your project now. And these boards will sometimes provide some flash, some extra RAM, and an ability to program. So in the case of that one in the middle there, the tiny FPGA BX, just plug your USB port in and off you go. It's amazing. So as microcontroller users, as I suspect many of us are, and certainly I was for many years, I got used to sort of settling for the peripheral mashup that some EE a few years ago had decided would be the right one for my application. And you don't have to do that anymore. That's just so great. If you don't like your one-wire SPI implementation on your microcontroller, make a 10-wire SPI implementation on your microcontroller. Just do that. If you don't like the idea of dropping down to Ethernet TCP/IP to do fast communications, don't. Use your own, and we'll get into that in a little bit. Write your own peripherals. And I was very pleased to see that the previous talkers hadn't focused on this too much, but there's this amazing expansion technique that you can use with FPGAs that haven't really found their way into the microcontroller world for one really good reason. They rely on the fact that every one of your microcontroller pins has a fixed function. So you can't use something like this where you would have on every pin, like, I want to put a I2C on this pin, I want to put a UART on this pin, and I want this pin to be GPIO. You can't do that with flexibility on a microcontroller. But you can on an FPGA, because every one of those pins is totally up to you how you want to use it. So as a consequence, there's this massive blossoming of modular hardware that can get plugged into these FPGA slots, and you can do all kind of amazing stuff. So just picking out a few at random here, we've got displays, we've got IMUs, microphones, push buttons, there's an ESP32 pressure sensor, and chip manufacturers are actually starting to get on the bandwagon now, especially analog devices. They are saying, well, why am I shipping an eval board with a microcontroller and all this other junk on it when I can just ship one of these little Pmods and someone can shove it into their FPGA situation? It's going to work really well. So I'm standing here to say, let's think about using these as our sort of modularity of expansion rather than the sort of ad hoc stuff that we've been forced to use as we're using microcontrollers. So how do we connect them with our FPGAs? We make baseboards. All of us can get into KiCad and make a simple connection between one board and another. There's no high-speed connections required, nothing fancy going on there. You can put little test pins on your boards if you want to. It's the way to go. Easy to design, cheap to manufacture, and you can configure it however you want. So in my advocacy role here, I'm saying let's use FPGA modules as sort of the thing that captures all the really hard layout and the hard work from a hardware point of view. Let's design or use baseboards that we plug these modules into that present the right inputs and outputs in the way that we want to use them. Let's design or use Pmods to do the modularity, and now we have a system that we can redefine later on, we can upgrade it, and we can play with it and share it. All these components can be separately shared. So remember, I was interested in doing networking in robotics, and one thing I'm always paranoid about is, my goodness, it's a noisy environment. It really isn't this pristine, beautiful environment that we're kind of used to playing around with. So I said, well, what kind of standards are out there? And it turns out there's this nice multi-drop standard called MLVDS. It's just getting started at 50 megabits per second and goes all the way up to a gigabit per second on 5 meter drops. So here's a little shot of my messy disk with some code that I wrote doing fast comms running on a tiny FPGA BX in the background, and that very same code running on a Xilinx FPGA on the front, and we're spitting 100 megabits per second backwards and forwards. As I say, completely effortless, no special traces, nothing hard to do there. It's just basically clock and data. It's like a very fast SPI link. This is one of my favorite little images too. So here I have two of my little Pmods which have these little interface boards on them, interface chips on them, and then they're running through 30 feet of twisted pair. And the little fuzzy thing in the background there shows the output signal, and then about 60 nanoseconds later coming back into the input again, having gone 33 round in length and being recovered very nicely. This stuff works great, and the code that I've got has got CRC protection on it, so you just basically throw a stream of data in, and out comes another stream. I don't have to worry about Ethernet. It's very straightforward. Another thing that we want to do in robotics a lot is analog I/O, and you may have noticed that a lot of FPGAs do not have an A to D on them. And in any rate, you wouldn't want one because it sort of defeats the purpose a little bit, because what we're trying to advocate here is bring all the logic onto the FPGA and then have your specialized hardware outside. So here you get to choose the A to D you want. So this is a super cute little chip. It basically is SPI in and then has 8 configurable ports on the output. So you can have inputs, analog in, it has DACs on it, so you could do true analog out, and then you can do GPIO. So those are super handy, and they're really nice little I/O expanders. How do you do motor control? Something that I said I was pretty interested in. So first thing I designed was based around some TI chips. They're basically 10 amps per channel for half bridges. So this board was designed to do either a stepper motor, 2 conventional brush DC motors, or a brushless motor. And then I added on a couple of shift registers, because again, with an FPGA, it's conceivable to run a shift register at 50 megahertz a second. You have full control of it. You just write that peripheral, super trivial to write. And we use the same technique to get digital input. So this board can read, can do fast PWM on all the channels. It can read analog inputs for feedback, for position. It can resolve a shaft encoder. Pretty much great motor control with 8 pins. So now that I've said my piece about hardware modularity, what about the code? And this is where it gets pretty interesting. So one alternative, and I think this is a great alternative, and everyone should definitely use this, is to put a little soft CPU on your FPGA, design your peripheral mix-up around the outside, and go for it with your new customized microcontroller. But there is another interesting way, and that is to say, well, what if I really focus on the Verilog side of things? What if I really wanted to take advantage of all of the ways that I can make basically all of this amazing 44,000 gates in the case of this FPGA? What if I can bring those all to work for me at once? Now, one of the problems is that Verilog is a very low-level language, and every person who writes their special Verilog module, myself included, has ideas about what they want their inputs and outputs to be, and quite often they do not connect together. When I did a little search for some fixed point math stuff, I was just shocked at how, first of all, crappy they were, and secondly, how you say, well, here's one that does it one way, and here's another one that does another way. They're completely incompatible. So you can't drop one in, drop the other one in. They just don't work together. So it's kind of annoying. So in a way to fix that, I'm going to advocate that we start to focus on making some more standardized connections between our Verilog modules. And I'm going to crave your indulgence to just run through this little example so that you get a feel for what I'm talking about. So in general, the problem is, if I have one Verilog module that's generating data, it could be a camera, it could be a microphone, it could be some kind of logic, and we have another Verilog module that's receiving data, we basically want to put a line between them and say that's our data line. Data's flowing between them, and that makes perfect sense. So over time, you could see, yeah, every now and again, one of those clocks is going to have some new data for the consumer. But there is a giant problem with this. You probably can all see it immediately. We don't know when the data is available. So what we do is we add this valid line which says, hey, consumer, we've got some new data. Please read that in. And that's great. That works really great. and that's all you need sometimes. But there's another problem. What if your consumer can't take the data as fast as you can give it? In that case, what you want to do is to have another line going the other way saying, I'm ready for data, or, you know what, I'm not ready for data. So here we're saying that for D1, both the consumer and the producer were both ready, so the data was considered to be transferred. Here for data 2, we say, yep, I was ready with my data, and the consumer was ready to receive it, so we're good, data transferred. But then look at period 8 here. The producer's ready, but the receiver's not ready, so the receiver's got a low line. So the producer just hangs on to that data until the receiver's ready. Now, this is a total stock standard thing. Like, there's a lot, I mean, so much uses this exact same standard, and yet everybody has different names for the signals. So I'm going to advocate for people stopping doing that and using the same signal names, because it's the same stuff. And I've created some tools to help with that. Not only that, but if you're in this situation where you're sending a lot of data, let's say, for example, you're sending a video frame, then you might want to know when your video frame starts and when it stops. So we can add another couple of signals to that bus to say, here's my first byte, here's my last byte. Now we really know when we're at the beginning and the end of the data that we're sending. And you'll see that again in a second. So I've done a lot of talking about the lines that I want to add to this sort of standard. But man, if you were to individually wire each one of those, for each one it's kind of a pain. So what I'm suggesting is that we put them all into one array where we have the data in the bottom and then we have these other signals in this one line. And then what you can do is you can actually just wire them up with one connection, A to B. And so our code starts to look more like something that we might hope for in software, where we have pipe out, pipe in, and we just wire it together. And that's exactly the way that the code that I've been writing works, and it works really well. So I was going to make this talk be all about motion control, because that's something near and dear to my heart. But when I saw that the badge was around and that it had such a nice graphics output on it, I said, well, let me try my hand at interfacing the camera. So taking these ideas that I've been trying to advocate, I built a pipeline which has the camera on one side, which generates, on request, generates frames. Another unit which says, hey, camera, you can send those frames as quickly as you like to me. I'll just store them until whatever it is back here wants them. And then I have another unit which converts the grayscale that the camera makes into RGB, which is what the LCD needs. And then another unit which will put rectangles of pixels onto the screen. So that's all in Verilog. You use the tools, Yosis, etc., to turn it into code. All of these pipelines are using these techniques that I just explained to you, that here's the starter frame, here's all the data. Feel free to stop me if I'm going too quickly, which in fact, the camera's way faster than the LCD unit. And you get images on your board. 7% of the FPGAs used doing this, so just let that sort of sink in. I could be doing this many times on this board. So if any of you have got this in their mind, man, video's so hard, it's so demanding, it uses up so much compute power, it's special silicon. You can kind of let go of some of those thoughts when you're using an FPGA, and you can start to think of things in terms of pipelines that do a lot of great stuff. And yes, if anyone was at the talk earlier, I was the respectful person who thought that this was Spoke's little watermark here, and I accidentally copied his logo, what I thought was his logo, onto my board, but anyway. So here's the cartridge board. I use this, I plug this into the board, and then I plug the camera into that, and I have one of my little Pmods there so that I can plug other things into that as well. And as work in progress, I have an image scaler on the way. I'm working on a Bayer, which is the color camera pattern to RGB converter, which will just drop into that pipeline. I've got some fonts coming, charting, multiplexes, etc., etc. So that's coming in these pipelines. So you just think about what you could start to build when you have access to that kind of technology. So I'm not here to tell you that it's all great either. So let's go into some wrinkles. FPGA development is actually quite hard. it's not like learning another programming language. You sort of have to do a little mental surgery. Took me about, 1 year I've been doing it, and I feel like I'm at an intermediate level now where I can do that kind of block. But man, I went through many loops of the swagger like, yeah, I got this. It's like C, I totally got this. It's like, oh man, I don't got this. I really thought I understood it, but I don't understand it. I went through that loop many times, and that was tough. But I think with more examples, better examples, we'll do better there. So you're developing in a strange environment, so you're not sure of the tools, you're not sure of the hardware. So it can be complicated in that way. Sometimes the tools are a little bit buggy, and they are frequently obtuse. And sometimes the tools can't get at all the features that you have on your FPGA. So there's some wrinkles there. Don't get me started on the state of the libraries. It is shocking. For 50 years, these EE people have been writing code, and they have left almost no trace that I can make. Now, you can go in, you could do a whole talk on the sociology of why that is. I think part of it's because of manufacturers with their special proprietary code preventing people from creating code that they could move around to other platforms. I think it might be partially because the EE mentality is not a sharing mentality. There's a ton of reasons. Anyway, it's extremely disappointing. Code is kind of crappy. Sometimes you'll be like seeing someone's code that they were like, yep, I'm kind of done, nearly finished, 2012. And you're like, what are you talking about? There are programming languages that have been invented in the last 2 years that have more libraries than we have available to us. So don't expect that you're just going to go looking in GitHub and find the magic code that you want. So I'm going to end with my MicroFPGA advocacy slide. Those of you who are into it, design us some nice, elegant FPGA module cores that we can use and just plug in. Give us some memory on there. Give us a nice connector that we can all work with. Those of us who are more into like the integration thing, design us some boards that have different Pmods and other kind of connection standards. Remember, these are cheap. We can just get them from a board manufacturer, solder them up with connectors, and we're good to go. Those of you who have specialized knowledge on motion control, radio, any kind of special signal path stuff, design us some Pmods that we can plug into this infrastructure. Those of you who want to write some code, write modular interconnected FPGA code. Don't write Ferraris, write minivans. If you're going to use soft CPUs, write some libraries for those that expect that you might be talking to Pmods on the outside. Don't just drop the Pmod in someone's lap and say, go for it, write your Verilog, deliver some libraries that work with it so people can get up to speed quickly with it. Yeah, here's one. Instead of us all just signing up for Ethernet and USB, when we don't need to use them, let's ditch them and let's write standards that are more appropriate, that are faster, and that dovetail nicely with the kind of hacker ethos. Those special chips that we're paying like $10 each that do advanced power management and have tons of registers and tons of control, let's ditch those. Let's put the special logic on a Pmod, the special electronics on a Pmod and bring the logic into the FPGA. Then we can innovate real quick on those. The algorithms inside them can have some kind of visibility. Stop using those annoying standards. Let's develop our own. Let's make them faster and better. Let's make products and projects that have upgradable hardware on them. And share your stuff. We have 50 years to make up for. Thanks very much.